So this was a game between the Cleveland Cavaliers and the Golden State Warriors. And this is the Cavaliers' estimated win probability throughout the fourth quarter. So he considered a number of variables such as point spread, score differential, time remaining, total points, home court advantage, who had the ball. And you can see this, so this is throughout the fourth quarter. So the game was tied going into the fourth quarter. It starts out, Golden State has about a 60% chance of winning. Kind of goes back and forth. Cleveland pulls ahead, then Golden State pulls back ahead. At this point, with about 5.5 minutes left, Golden State went up by 4, so their probability is at about 70%. Cleveland's is only about 30%. You can see Cleveland comes back then. And then if you watch that game, you might remember the strange thing about that game was nobody scored for about 4 minutes here. And so you can see just some little jumps between who had the ball. And then with just under a minute left, Cleveland, Kyrie Irving made a three-pointer that put them ahead, and so their probability jumps from about 40% to 70%, and then they go on and win the game. So it's an interesting graphic that Dennis put together using random forest to estimate the probability that the Cavs would win that game. So you can see random forest can be used for all kinds of things. Now, I grew up just outside of Cleveland, so I had to include this example in the slides.
And can you do that live during the game?
Yeah. So Dennis actually, during the Super Bowl a few years ago, live blogged his probabilities throughout the game. Unfortunately, it turned out to be a really bad Super Bowl where Seattle fought with Denver, and so it just pretty much went like, Seattle's probability went to like 90% in the first quarter and then just stayed there. But yeah, Dennis does.
Has this model been validated in the sports betting arena? That every time it goes above 50%, you bet on them winning, and was below, you bet on them losing. And
yeah, depending on what kind of odds you're getting. I would be interested to look at. Now, ESPN does all kinds. I mean, you can go on ESPN during a game, and they'll tell you this sort of thing. I don't know. I don't think that they're using random forest to do their sort of thing.
I mean, that would be one way of telling whether or not random forests were a superior way of predicting compared to the others that are out there.
That's true. That's a good point. Let's see how Rich Dennis thinks. But yeah, that's an interesting way. Okay, so the last thing I want to talk about is some research that I'm doing pertaining to outliers. So outliers can be an issue in almost any kind of statistical analysis. So what I've done here is I've plotted for 2014 math, CS, and stat majors the first semester GPA that our random forest model predicts the student should have against the student's actual true model. And the line you see there is the line y equals x. So if our predictions were doing great, they would be right on that line. It's hard to say. I mean, we're doing okay. It's hard to really quantify the performance. But the point I want to draw your attention to is this drop down here. So we got a student that we projected should have had a first semester GPA of about 3.4, and the student's GPA was less than 1. So I think we would call that an outlier. Maybe something happened in that student's life that impacted that. We don't know. But that's a concern. So in our data set, we call this student number 39. And I'll mention, so this is based on a real situation, but all the information I'm showing you here is fake to protect the student's privacy. But here's some information on that student. And now let's suppose a new student comes along. And if you compare these students, they happen to look a lot alike. And so when the random forest goes and tries to make a prediction for this new student, it's going to say, hey, this student looks a lot like student number 39. So I'm going to look at how student 39 did when I predict how this new student's going to do. Right, and just to look at how a random forest would do that, so I'm going to go back to a graph that I showed you before. I can actually trace back the weights of each individual training case and look at how much that's contributing to a new prediction. So for instance, this response 3 is accounting for 1/3 of the prediction in this first tree, 3/4 of the prediction in the second tree, and 0 of the prediction in this third tree. So if I average that, in this picture, this response 3 is accounting for 36% of the prediction for this new case. So now I can go back to my case with those students, and I can look at how much weight each student is giving to this new student I'm trying to predict. And if you look at it here, student number 39, who had that 0.88 GPA, is accounting for 19% of the weight that's going into predicting my new student. And so then, when I compute this random forest prediction, all it boils down to is the product of the GPA here times the predicted, or times the prediction weight. And when you compute those, it turns out that the prediction for the new student is that that student will have a 2.95 GPA. But if I look at most of the students here, most of them are higher than 2.95, and it's this one student 39 that's really dragging that prediction down. So I've got this strange case, this outlier is having a heavy impact on my prediction. And I may not want that. So here's what we call a residual plot. I plotted the difference between the actual GPA and the predicted one against the actual, or the predicted first semester GPA. And here's that student who was more than 2 points lower than we predicted. And there's some good reasoning to say that maybe when we have a really large residual, maybe there's something strange going on there. Maybe we ought to be dubious about that point, and there's some statistical theory in some cases to show that we ought to downweight cases with large residuals and have them count less towards our prediction. So that's what we tried to do here. So we've come up with an algorithm, and this is modified by an algorithm that was originally proposed by a statistician named Cleveland in 1979 on a paper dealing with locally weighted regression scatter plot smoothing, which is sometimes abbreviated LOS. And we're trying to apply that to random forest predictions. So to summarize quickly what we're going to do, we take each residual, and then we find the median of the residuals. And then we come up with, we apply this function, so this is called a Tukey by square function. Basically what this does is the farther away it gets from 0, the less weight it has. So if I plug 0 into this function, I get back 1. If I plug in a number farther away from 0, I get less and less. And if I'm outside of the range from 1 to -1, it's 0. So this is telling me how much weight I should give my new case. And then I re-weight and I rescale. So in this case, I'm going to multiply my original weight of 19% by this value that came out of the Tukey by square function, and I get a weight of about 0.005.